Good day, class. Today I want to continue on with our discussion of Chapter 7 and introduce a couple of other concepts in thermochemistry. And one of those is this notion or this idea called standard conditions. Now, we've dealt with this before a little bit, and we talked about gases, right? And we talk about standard conditions, or standard temperature and pressure for a gas, right? 1 atmosphere, 0 degrees Celsius. So we have standard conditions. So standard conditions can be sort of applied to all forms of matter, and they're defined in the following way, right? So what we call the standard state of something is if it's in a gas, then it's a gas at exactly 1 atmosphere pressure. If something exists as a solid or a liquid, it is whatever its most stable form is at 1 atmosphere and 25 degrees Celsius. So the way we look at this, right, is that we have some material. Its standard state of existence, gas, liquid, or solid, is going to be whatever it exists at 1 atmosphere of pressure, essentially. Right? If it exists as a gas, then it's going to be that gas at 1 atmosphere of pressure. If it exists as a solid or liquid, it's going to be, its standard state would be whichever one of those it exists at 1 atmosphere and 25 degrees Celsius. Now, if we're dealing with a solution, the standard state for a solution is 1 molar concentration. Now, when we deal with these thermodynamic quantities like enthalpy, right, when we're calculating them like we did in the calorimetry problem, we were not at standard state, right? Notice those concentrations were not 1 molar. Right? So the enthalpy change that we calculated was not a standard enthalpy change, right? It was the enthalpy change under those conditions. Now, there are what we call standard enthalpy changes, and those are indicated by the enthalpy change, but the key is the little degree sign there. So when you have the degree sign there, that means that we're dealing with the value at standard state. So it's the enthalpy change when all the reactants and products are in their standard states. That's what we call the standard enthalpy change. Now, the way these standard enthalpy changes for reactions are calculated is by looking at something called standard enthalpies of formation. And so when we have that sub F here, this means we're dealing with a specific kind of enthalpy change, and this is the enthalpy of formation. Now, what does that mean? Well, an enthalpy change of formation is the formation of a compound from its elements. More specifically, it's the enthalpy change involved in the reaction to form 1 mole of some compound from its constituent elements. Now, when you start to look at these, you may see some things that look weird because we start to have fractional coefficients in some of these equations, the formation equations, because it's the formation of 1 mole. So, for example, if you wanted to, if you look at, say, CO2 on here, the value here, the delta H of formation is negative 393.5. Well, that's the value for this reaction. Carbon plus half a mole of O2 goes to 1 mole of CO2. Right? And so this is the enthalpy change for this reaction. The reaction of 1 mole of carbon plus half a mole of oxygen, plus 1 mole, not half a mole, 1 mole of oxygen to give CO2. But if you have something like CO above it here, it's going to be carbon plus half a mole of oxygen to give you a mole of CO. And so that negative 110.5 kilojoules is formed when you react 1 mole of carbon plus half a mole of O2 to give 1 mole of CO. So the reason that sometimes they're written like this when you read the book is that when they talk about these enthalpies of formation, you're restricted to forming 1 mole. And so we can't have, always have whole number coefficients like we would in a real normal balanced equation. So just a little side there of what you might see something. Now, the reason these are important, right, is because we can look at these formations and use these different delta H's of formations to calculate the enthalpy changes for reactions. Now, in the chapter, they have this sort of relatively small list of standard enthalpies of formation. Notice these are in kilojoules per 1 mole, right? Just like I said. And this delta H sub F. Now, in the back of the book, in the appendix, you'll find a much larger list. So if you can't find something in the table, look in the appendix for the listing of thermodynamic data, and you'll see a column for delta H sub F, and you want to look at that. Now, be careful when you look at this because they may have the same material on different states of matter. So you just need to be a little bit careful in how we look at this. So you just want to make sure you're pulling the right material. So for example, we have 2 forms of carbon here. Sometimes when they list water, they'll list water as a liquid, water as a gas. So you just want to be careful that you're pulling the right material. So how do we do this calculation? So let's say we want to calculate the delta H standard state for a reaction. And we want to use these enthalpies of formation to do it. Well, any reaction can be written as the sum of formation reactions or the reverse of formation reactants if we have the reactants, right? If we're, the deformation or the decomposition of the reactants is just the opposite of the formation. And for the products, we have the formation. So the general equation that we can use to calculate this is to look at the sum of all of the enthalpies of formation of the products. Now, this N here is how many moles are in our balanced equation, right? So remember, these formation values are per mole. So if we're reacting 2 moles or whatever, we have to multiply by the coefficients. So N equals the coefficients in the balanced equation. And minus the sum of all of the enthalpies of formation for the reactants times their coefficient. So notice the way we're setting this up is the change equals the final state minus the initial. So just like when we do change in temperature, change in volume, right? It's always the final state minus the initial state is our change. Products here being our final state, the reactants being our initial state. So let's look at this reaction. So over here I've given you a partial list of pulling from the table. So these just come out of the tables. So when I say write this, I'm going to do my products first. So it's going to be the sum. So it's going to be 3 times the delta H of formation for CO2 gas plus 4 times the delta H of formation for H2O gas So this is the products part minus one times the delta H of formation of C3H8 as a gas. Now, notice we have the O2, but remember, for elements, they're going to be zero, right? Because the formation of an element is forming it from itself. So if I wanted to have the delta H of formation of O2, right, it would be 1/2 mole of O2 B. It's going to be O2 going to O2, right? So there's not going to be any change. So remember it said on the last slide, the delta H of formation for any element equals 0. So we could put it in here, but it's going to be a 0 value. Okay, so we have our products minus our reactants. So now we just matter plugging in the numbers. So we got 3 times the delta H of formation of CO2 is negative 393.5 kilojoules per mole. Now notice our moles are going to cancel it because this is really 3 moles, right? When we have our coefficients here. Plus 4 times water, negative 241.8 kilojoules per mole. Minus 1 times negative 103.85 kilojoules per mole. So then we go through here. And we get our calculation, and we get negative 2147.7 kilojoules minus 103.85 kilojoules. We do the math, so this, we can make that plus, so we end up with minus 2044 kilojoules is our delta H reaction. Now, you might recognize this number because we had this equation earlier on an earlier slide, and this value was given to you as the delta H of formation for that particular reaction when we talked about enthalpy. Now, notice it's not kilojoules per mole, right? This is for the balanced equation, right? So remember, our moles cancel out here because we're really multiplying this by the coefficients, which are the number of moles. So this is like 3 moles times this, so our moles cancel. And so we end up with just the kilojoules for whatever my balanced equation is here. Okay. So this is how I can use the delta H's of formation listed in the back of the book to calculate my standard enthalpies of reaction by taking products minus reactants. So this becomes a very useful tool.